Hello everyone. Once again, it's a pleasure to welcome you all to MSP lecture series on interpretative spectroscopy. In my previous lectures, I started discussing about NMR spectra of various phosphorus containing compounds, and also how to analyze if you get more than one product in a reaction. For example, if you get cis and trans isomers, or if you get some other isomers, we should be able to elucidate and understand the structures of those molecules by simply applying phosphorus NMR spectroscopy. So let us continue from where I had stopped. Let me take another interesting reaction here. This reaction, you can see I have used two entities. One is cyclopentadienyl bis triphenyl phosphine chlororuthenium 2+, that is reacted with bis diphenyl phosphinoamine ligand. So that means in this reaction, although we know that when we are mixing in a known stoichiometry, we are supposed to get one product, but on the other hand, due to some reactivity difference that we gauge, and that's what happens later, we end up getting more than one product. So that means we may get a mixture of products as well. In that case, if we analyze by looking into the 31P NMR spectrum of that reaction mixture, that can tell you a lot more details, and also that can also guide you how to plan our reaction by altering reaction conditions. For example, in this one, as I said, this ruthenium 2 compound was treated with this bisphosphine. In the above reaction I have shown here, we are getting three products, 4, 5 and 6 in different stoichiometries. Although the reaction is carried out in 1:1 ratio, the expected product is 4. But how other two compounds are formed and how did we got this information, that one can see by simply looking into the 31P NMR spectrum of the reaction mixture here. Several chemical shifts are there. But if you recall the first compound 4, where 2 triphenyl phosphines are replaced by bisphosphine. So here both the phosphorus environments are identical. As a result, one can expect a single resonance here. That means this is assigned to the product 4. Now let us look into other products. Let us go back to the reaction. In this product 6, one triphenyl phosphine is there and one bisphosphine is there. Bisphosphine chemical environments are identical, and we have PPH3. So by simple thumb rule, by looking into 2Ni+1 rule, we can anticipate a triplet for triphenyl phosphine and a doublet for bisphosphine, because bisphosphine will be coupled with both of them together, coupled with the triphenyl phosphine, whereas triphenyl phosphine will be coupling with the 2 equivalent phosphorus centers from bisphosphine. So we expect a triplet and a doublet for 6. So you can see here a doublet is there and a triplet is there. This is for triphenyl phosphine and this is for chelated 2 phosphorus moieties of bis diphenyl phosphinoamine. So then we have left with one here, one here, one here for product 5. So what is that product 5? So product 5, if you see, we have one dangling phosphine is there acting as a monodentate ligand. So this is different and this is different, and these two are identical. So that means we are anticipating 3 signals, and here this phosphine is farther away from bisphosphine. As a result, this can just couple with coordinated phosphorus to show a doublet. But on the other hand, the chelated phosphines also can couple with coordinated phosphorus from the monodentate ligand to show a doublet, whereas this one would show a triplet with this one, and a triplet is further split into doublets from this one. That means we are seeing a multiplet for monocoordinated phosphorus and a doublet for bis coordinated or chelate compound, and then again doublet for this one. So let us see whether we have those things here. Yes, we have a doublet, and we have a doublet with very small coupling constant value, and also we have a multiplet here. It is a triplet of doublets. So we are seeing that one. So that means this is giving some idea that 3 compounds are formed, but again looking into the integration, we can gauge how much quantity of each one is formed in what ratio, and then looking into other 2 compounds where ionic products are there. Yes, that means probably instead of using, let us say I have used dichloromethane here, instead of using dichloromethane, if I use a polar solvent, probably the formation of 4 can be diminished and formation of these 2 compounds can be enhanced yields. On the other hand, again by taking 2 stoichiometry, 2 equivalents of bis-diphenylphosphine, probably I can enhance the possibility of formation of 5 even more. So this vital information comes for using those information. So this reaction was carried out and this pure compound was obtained, carrying out at low temperature, and then by using 2 equivalents of bisphosphine in polar solvent resulted in this compound, and then using a polar solvent but 1 equivalent of bis-diphenylphosphine used resulted in this compound. Of course, once after making this compound, if you bubble CO here, this can form a carbonyl compound. So this all vital information comes very nicely by analyzing the 31P NMR spectrum of the mixture of this reaction product. That means it is not just to analyze and understand what kind of compounds formed, it can certainly help us in altering our reaction conditions so that we can refine our methodology. And later all these compounds were prepared in pure form and analyzed. You can see here, so these compounds were formed, and then this compound was again prepared in a separate reaction by getting the information from the reaction mixture, and then this was obtained in pure form. And now let us look into few more examples here. I have given 3 examples here. One is a bisphosphine with both the phosphorus oxidized by selenium, that is bis-selenide derivative here, and then I have here analogous to Vaska's compound, both cis and trans, chlorocarbonyl bis-diphenylphosphine, bis-triphenylphosphine rhodium, and also its cis analog. And they differ significantly in their 31P NMR spectra. First, let us look into bisphosphine here. Of course, when we look into bisphosphine with both the phosphorus oxidized by selenium here, 31P NMR spectrum would show a singlet, and then it is coupled to selenium, 77 selenium, and that shows satellites here. Separation is called phosphorus selenium coupling constant. So these are called satellite peaks. And then if you look into selenium NMR, again both the selenium centers are chemically and magnetically equivalent. As a result, they are equally coupled to phosphorus, and we will see just a doublet. And then this, whatever the separation is there here in case of selenium NMR, should be same as what we obtained in case of 31P NMR. That means coupling constants remain same no matter which nuclei you are using. Now let us look into trans compound here. In case of trans compound, you can see both the phosphorus are identical by performing a C2 axis of rotation passing through CO and Cl. As a result, you can see only one type of phosphorus, and when you look into 31P NMR, they are simply coupled to rhodium to give a doublet here, something like the very simple doublet is here, and then this separation is called 1J RHP. But when you look into this one here, one triphenylphosphine moiety, here it is triphenylphosphine. One triphenylphosphine is trans to CO, whereas the other one is cis to CO. So we cannot have C2 axis of rotation. As a result, 2 phosphorus atoms are chemically equivalent, but they are both chemically and magnetically non-equivalent. As a result, it resembles AMX spin system. So Pa is coupled with rhodium and then coupled with phosphorus. It shows a doublet of doublet. In the same way, Pb is also coupled first with rhodium, and each line is further coupled with phosphorus. So first this is rhodium coupling, and then this is phosphorus coupling. Whether you consider Pa, delta of Pa or delta of Pb, they are very similar, but slight marginal difference is there in chemical shifts and coupling constants. So this is rhodium phosphorus coupling, and then here it is 2J PP coupling. So this is how we can distinguish cis and trans isomers in case if they are obtained in a reaction. Let us look into two more examples here. And we have a mixed ligand complex, platinum 0, a tetrahedral complex where we have 2 trimethyl phosphine and 2 diphenyl phosphine. So that means platinum is in +2 state here. 2 trimethyl phosphines are neutral ligands, and here we have 2 diphenyl phosphines. Phosphides are there, they are anionic, so platinum is in +2 state and it's a 16 electron complex. So now if you look into phosphorus NMR spectrum, we can anticipate 2 type of signals. So these two are identical, they are coupled with these two to give a triplet. These two will couple with equally to this one to give a triplet, and then these two will couple with this one to give a triplet. So what we should get is a triplet, something like this, and then platinum coupling would come. So basically platinum coupling would come with platinum satellites because of 195 platinum is about 34% NMR active, I equals half. So as a result, this is for 196 platinum, which is I equals 0. So then what we get is this is split into a doublet here, something like this, and then something like this. So if we look into the spectrum, it should look like this distance is called 1J PT-P coupling. This is similar for both of them. This is similar for both of them. Whether we consider a signal for trimethyl phosphine or we look into that one, they will be identical, but they will be having different chemical shifts. Here, this one is for 196 platinum. And then if you look into the integration, this would account for 66%, and then this would be 17%. And then this is 17%. So this is how we can analyze the spectrum, and you can ignore this spectrum here, you can ignore this one, and of course you can also look into 1H NMR spectrum here because trimethyl group is there. And this trimethyl group, what happens, this is, of course, here you can see both are identical, both the trimethyl phosphine groups, and CH3 first it will be coupled with phosphorus to give a doublet, and then each doublet something will be there, rhodium to hydrogen coupling, and then we will see a hydrogen to platinum coupling will be there, something like this again. So this is how the 1H NMR would look like. And most of the time by default when we are looking into phosphorus NMR, what we get is proton decoupled one. And of course if we are interested in looking into phosphorus hydrogen coupling, then we can go for coupled one. In that case, it should be represented something like this. The moment we write in flower bracket next to phosphorus 31P, it indicates that 1H is decoupled, and that means interaction of hydrogen protons in the magnetic field when we are measuring phosphorus NMR is nullified. So now I have another interesting compound here. In this one, it's a dimetallic compound here, and 2 platinum atoms are there. At terminally, they are held by 2 trimethyl phosphine each, and the middle we have diphenyl phosphide ligand is there. So both the platinum, if you take symmetric, it will be 1 1, or it can be one side it is platinum 0 and one side it can be platinum 2 also. So now we can look into the spectrum of this one here, how it looks like. Let me write the structure again here. This is about 195 platinum NMR. First we can look into 195 platinum NMR. This is the structure. So now if you see these platinums are both chemically and magnetically equivalent. Both the platinums are coupled on either side by 2 different type of phosphorus units. So here let us say first this is coupled with 2 phosphorus units, and if you just look into 2Na+1, it should be a triplet, and then this separation or this separation would be 1J PT P, I should say PPH2. And now each of these signal will be further split by 2 end trimethyl phosphine. So this will be coupled with first these 2 and then these 2. So this separation is 1J PT, P, Me3. So it shows a triplet of triplet, and if you look into the spectrum, it should look like 1:2:1. Something like this. So this is how the 195 platinum NMR looks like. But on the other hand, when we look into phosphorus NMR, if you look into it, these two are identical and they are equally coupled to 4-trimethyl phosphine. As a result, what would happen? Delta PPH2, let me write here, it will show first a quintet, so it should show a quintet, and then each quintet is further split into a doublet in the form of a satellite. So as a result, what would happen is we get something like this. So something like this. Again, this is for 66%, and then this is 17%, and this is 17%, and then distance from the middle one to mid one or first one to first one, this is called 1J PTP coupling, and this spacing is called PP coupling. PP coupling, this is how you can write it. But on the other hand, this would give a, this one, these two are identical with this one. When they are coupled with this one, we get simply a triplet, and then this triplet is split into another doublet because of platinum coupling. So this would be something like this. Something like this. Again here, this is your 1J PTP coupling. Okay. So this is how the spectrum can be analyzed. So now let us look into other applications. We have several applications. There one very important application I am going to show you, especially those who are working with nanomaterials and working with carbon compounds such as fullerenes, graphenes, graphene oxides, and other things. Very, very important one. Measuring epoxide content of carbon nanomaterials. The presence of epoxide on nanomaterials such as carbon nanotubes and fullerenes can be readily monitored by reacting these nanomaterials with triphenylphosphine. How it helps in understanding the presence of epoxide? So this method involves the catalytic reaction of methyl trioxorhenium. So an epoxide reacts with methyl trioxorhenium to form a 5-membered ring, and in the presence of triphenylphosphine, the catalyst is regenerated, forming an alkene, and then formation of triphenylphosphine oxide. So when we add triphenylphosphine along with methyl trioxorhenium to nanomaterial containing epoxide, oxygen is abstracted by triphenylphosphine to form triphenylphosphine oxide by simply taking the known quantity of triphenylphosphine, and by monitoring the 31P NMR spectra at regular intervals, we can quantify the amount of epoxide present by looking into the amount of triphenylphosphine is converted into triphenylphosphine oxide and how much is left at the end of the reaction. So this is the reaction. For example, we have an epoxide is here, and epoxide when is treated with methyl trioxorhenium, it forms a cyclic system like this, and when this cyclic system is treated with triphenylphosphine, it abstracts oxygen from this oxocyclic system to form triphenylphosphine oxide and regenerating methyl trioxorhenium through the formation of this olefin. So now exactly this is what happens. So for example, we have on graphene, we have epoxides are there, you just treat with this one, and then as I said here, triphenylphosphine abstract, and this one is regenerated, and then by simply looking into the reaction mixture NMR, we can conclude that yes, since the amount of PPH3 used in the reaction is known, the relative amounts of triphenylphosphine and triphenylphosphine oxide can be determined simply by looking into the integration of 31P signals in the spectrum, and that in turn gives the amount of epoxide present on the nanotubes. So this is very, very important, very simple reaction. One can analyze and also one can also get rid of all these epoxides if they are not readed. So you can see here 31p spectra before and after the reaction. Before the reaction, the full quantity is there, and now after the reaction, what happens? Partially ppH3 is converted into triphenyl phosphine oxide depending upon how many epoxide groups were present on nanomaterial. So then if you just look into the integration, now only 0.4% is left. Let us say if we have used 2 equivalents, 1.6 is converted into triphenyl phosphine oxide, and now only 0.4% is left in the solution. So that gives how much is there in it. This is a very, very important method one can use effectively for determining epoxides present. So let me stop here and continue with more interesting examples in my next lecture. Until then, have an excellent time reading spectroscopy. Thank you.